Apologies for the delay in starting this particular presentation. What I'm going to talk to you about today, thank you all for coming as well. I know it's late in the day and it's been a hot day. So what I'm going to talk to you about today is using LIDARs for geo solutions. And we're talking, let me just go on to the next bit. So as a presentation outline, I'm going to do an introduction of who Sentek Solutions are, who Hokuyo are, who are our supplier and manufacturer. I'm going to talk a little bit about what are laser rangefinders, what are LIDARs, in a very sort of general terminology. Then I'm going to talk something about the usage in the geo sector, summarizing in some points as to what the advantages of the Hokuyo devices, and then go on to some questions. Sentek Solutions Limited is the European distributor of Hokuyo. Hokuyo are a Japanese company, quite a small Japanese company, but with a very large impact in the industrial automation sector. They specialize in the manufacture of optical electronic devices. These include photoelectric cells, which is really where they started from, and other types of sensor in that area, moving through to optical communication devices, where instead of having wires connecting two different points and sending signals through those, you actually send signals and communications through a optical signal, one through a transmitter, the other to a receiver. And they're used in a variety of different areas for semiconductor manufacture and also for warehousing and logistics. Finally, the area that they sort of happened across, I suppose, probably 15 years ago, 10, 15, 20 years ago, was laser rangefinders and associated devices, which have culminated in the LIDARs that we see today and the safety scanners which are used. The areas of operation, or the markets that Hokuyo and Sentek Solution operate within, industrial automation, which is really where the background of all the Hokuyo products comes from. So this includes automatic guided vehicles, some of the warehousing systems that are available. Port technology, where LIDARs and optical data communication devices are used for control and automation of port areas. Semiconductor fabrication, where robotics or automated vehicles are required because of clean room conditions and have been required for a long period of time. In that area, again, optical data transmission devices are used, and the laser rangefinders or LIDARs. Mobile robotics, UAV, so UAV of different types, and also the mobile robotics that we're familiar with today. So that, to a degree, has become one of our major markets, including industrial automation for this particular product. Security, as in making sure that nothing comes close to areas of value, and also, to a degree, making sure that humans don't come into contact with fast-moving, high-weight, high-momentum machinery. And finally, into the sector that we're talking about today, which is really the geo sector. which we've sort of happened into, I could say. So what is a LIDAR, or a laser rangefinder as we call it? The principle is simple. We have a moving or rotating class 1 infrared laser and a receiver. Class 1 is important because otherwise, if we start going to higher levels of laser, then it creates problems as far as eye safety is concerned. Once we get to class 2, then staring into a class 2 laser can cause problems with sight. So it has to be a class 1 laser, and we tend to use, or what's tended to be used in this area is an infrared laser, which is invisible, so you don't actually see the laser beam, which is important. It is important that we use the class 1 for obvious safety reasons, but if we were to move to class 2 lasers, then the job would be a lot simpler and we would get a lot better performance, but that's unfortunately something that we can't do. We have to use a receiver to actually receive the signal. We use 2 different types of technology, which I can show you a bit later if you're interested. One of which is, and the original technology that Hokuyo used was something called amplitude modulation, which looked for the phase lag of the wavelength that was reflected back. So a laser beam is shone onto a surface, it's reflected back, the reflected beam is then sensed and is analyzed, and by looking at the phase lag, you can detect the distance, or you can calculate the distance. Nowadays, a lot of LIDARs have moved towards using time of flight, where a digital pulse is put into the laser beam, and then it's looked to see when that digital pulse comes back, and you work out the distance from that. Then the other parts of the LIDAR, laser rangefinder, is having appropriately paired optics. Now, Sentek or Hokuyo have concentrated specifically on miniaturizing and making these devices as small as possible. And this has meant that the optics that they can use to magnify the level of the beam are minimized. If you increase the size of the device and you increase the size of the optics, and you increase the size of the scanner, then the job is made more simple. But of course, everybody wants a smaller device rather than a larger device. So you need to have appropriately paired optics. Our longer distance lasers, laser rangefinders, are unfortunately bigger, which is not what the market wants. They'd prefer them to be smaller, but that's a factor of life, unfortunately. You then need smart electronics to process the signals that are coming in, and some clever software to actually produce the data and in a format which is usable by robotics and also by industrial automation, or in this sector in geo. Everything's packaged in a protective housing, and one of the things that the Hokuyo devices, because they are so small, the protective housing is actually a functional part of the structure, and therefore these devices are very sensitive to people messing around with the housing, or trying to change optical windows, or trying to fiddle around internally. So there are more than 2 types of laser rangefinders, LIDARs. 2-dimensional LIDARs, which are really what we're involved in mainly, where you have a simple rotating beam. So you have a laser. So here is one of our laser rangefinders here. And this is probably almost about the smallest one that you'll find available in the market. So you have a laser, small laser diode, which is pointing down here. And then you have a motor at the bottom with the electronics at the bottom. There is a mirror on the rotating motor, which deflects the laser beam outwards. And then there is another mirror below, which deflects the incoming or reflected laser beam down into the sensing electronics. So this is about, as I said, about as small as you can get physically at the moment. Hopefully we can get smaller, but this is about as small as you can get for a laser rangefinder. And as you'll notice, the optics is just a window. There's no magnifying here. As you go to some of our larger devices, longer distance devices, then they're slightly bigger, and the optics and the sensitivity increases. The other types of LIDARs that you can find, which you'll see around the show here, are three-dimensional, multi-layered beams or multiple synchronized axis beams. So they have beams which are on different levels. So instead of producing a two-dimensional profile, then you produce several, so you can then produce a three-dimensional profile over the area that those laser beams operate. The other thing is having synchronized beams working in different axes, and that then produces a different level of 3D. As I've said before, Hokuyo have sort of happened upon this particular market. Excuse me, there's a transition on here, obviously. Originally, these devices were designed for the Japanese industrial market. All the Hokuyo devices were. And therefore, they are specifically very different from what you see in the European market. In the European market, there is a lot of difference in the robustness, the size of the lasers that are available, and also in the fact that there's been a focus on safety legislation which wasn't present in the Asian market. So you see a lot of safety scanners from which LIDARs have been derived in the European market. So the Hokuyo scanners that you see are generally two-dimensional, and the market has been segmented, as according to the Japanese market, into laser rangefinders, which are LIDARs just providing data, so an angle and a distance, and obstacle detectors, which are more dumb units where you can program specifically areas of exclusion, and then if something goes into those areas of exclusion, then they fire different outputs. Obstacle detectors begot safety scanners. Safety scanners are effectively the European equivalent of obstacle detectors, apart from the fact that obviously they have extra safety features and extra redundancy, and Hokuyo have now developed into that market. The Hokuyo focus has been on the size of these devices, hence the fact that we've got the smallest ones, the weight, and the power consumption. Hopefully this doesn't transition again. So different brands have had different approaches to these different markets that they've targeted. So the ones that you see in the geo sector are Velodyne, Regal, as examples of the 3D devices, which are total 3D devices produced specifically to make accurate maps. These tend to be a lot larger, a lot heavier, a lot more greedy on power than the small devices that Hokuyo make. SICK and other companies approached the market from a different angle, so they were producing industrial devices which were more robust, which were larger, which had safety features. Hokuyo approached the market from being small, light, customizable, and scalable. So they all approach the market from different angles, and to a degree what's happening now is everybody's going into different market sectors, one way or another. So they all approach it in different ways. SICK has produced the TIMs, which are sort of, they would like to think, equivalent to the Hokuyos. I guess Velodyne, Regal, and people like that are not going into the industrial market, so that's not happening. Hokuyo have produced safety scanners, and they're moving into the higher level market. And almost by accident, Hokuyo have moved into the geo market as well, which I'll expand on in a minute. So focusing on the geo market, so we talked about the 3D LIDARs, which they provide effectively an out-of-the-box solution. So you buy a Regal, you buy a Velodyne, and it will provide you with a beautiful 3D point cloud of what you're seeing. So it'll produce nice information, but it tends to be, as I've said before, tends to be heavier, tends to be significantly more expensive, which limits the areas that it can be used in. With the Hokuyo devices, customers have used, so our customers have generally created geo solutions using our Hokuyo LIDARs as components, as building blocks to develop sort of niche market solutions. So for instance, as you go around the exhibition here today, you will have seen things like GeoSlam. GeoSlam with the Revo and the Zeb, handheld solutions where you're using a Hokuyo laser to produce not the same sort of quality as the Regals or the Velodynes, but something where you can make mapping, 3D mapping, a lot more accessible as far as being able to do it because it's mobile, because it's light enough to carry, and being able to afford it and use it in more everyday situations and solutions. So things have become more affordable, more mass market, and I say comparatively. If I go into the industrial automation sector and I say, do you want to buy one of these devices and it's going to cost you between €1,000 and €4,500, they'll say, I'm not paying that amount of money for something like that. If I go into this market and say, or GeoSlam go into this market and say, pay however much they charge for it, 8,000, 10,000 euros for their devices, when they're compared with the Regals and things like that, then it's peanuts. So it's different levels for different markets. So yes, they become more affordable for this particular market sector where the entry costs are a lot more expensive. And because we're using these sort of devices, which are very light, so this one's 130 grams, the one on the Revo is less than 300 grams, then they can be used on drones and therefore UAV compatible. The next thing that the market is going towards is automation. So instead of having something on a drone where you control the drone, you move it round, it does the mapping, or you have a handheld device, you walk around. The next thing that the market is going to is combining the robotics with the mapping so as to have an automated robot which will go round, and there are a number of our customers that are looking at not just using these sort of devices for the digital mapping, but also using these sort of devices for the control functionality. So they have concepts, for instance, of going into supermarkets and being able to go round a supermarket with an automatic, so at night when the supermarket is closed, although not many close nowadays, but at night when they close, then you set the robot up, it wanders around the aisles, it navigates its way around, it takes a map of what's there, and next day or later on, you can tell what stock needs to be replenished in what shelves and things like that. So these are the next steps that are going to happen. So you're not just taking the 3D information, you're also taking you're using these sort of devices for automation as well. So a risk of sort of repeating myself here and sort of covering old ground, really. So what are the applications and challenges? So mapping 2D or 3D, you need to do this, then you need to have external localization. So these are the things that people like GeoSlam and Navis and people like that are doing. So they have to put this information into the solution because this is just spitting out raw data, okay? And the way that I always look at it is when you, although some people will not remember these days because you're a lot younger than me, but when you used to take photographs and you used to take panorama photographs, you used to sit on a beach and you used to try and get a photo of here and then a photo of here and a photo of here. And you try not to move, but whenever you got those photos back and you tried to put them all together, they'd never fit together. So the difficult thing with trying to use a two-dimensional laser, or any one of these sort of devices, is trying to take the data that's two-dimensional and glue it all together to get three-dimensional. And to do that, you need to know exactly where you are, which is easier when you're outside because you can use GPS. So you can position yourself. It's a hell of a lot more difficult inside because you can't, okay? It's easier when you've got a total solution like the Regals or the Velodynes because everything is mounted so it all synchronized and it's all in the right position, okay? So when you're taking something like this, then you've got to somehow glue the things together. So it makes things more difficult. So you have to have the GPS, you have to use altimeters for drones, so as to tell which height you're at. You have to use inertial sensors, accelerometers, et cetera, et cetera. Internally, as I say, things tend to be more complicated, so you try and use things like odometry. So when you're moving a robot, how far the wheels move, but then you assume that the wheels move perfectly on the surface, which they don't. So you have to try and sort of eliminate the errors there. What are they used for? Inspecting and surveying. You guys know all these sort of markets, but there are some areas that possibly you don't know of, like, for instance, using these sort of devices for these 3D mapping devices for things like inspecting the outside of planes. That tends to be a hell of a time-consuming and expensive operation if you think about how long it takes. If you could put a drone next to it, looking at infrastructure and providing autonomy, as I talked about, so robots that move around by themselves, which is not really a geo area, but another area where our devices are used. Limitations to use. All these devices, whichever they are, have limitations. And the limitations are the physics of light. They all work by reflectance of light. So they can't see through things. They can't see through objects, so if you're standing in front of this device, then you can't see round it. Same is true with any of the 3D devices, whatever. They can only see what's in front of them. They can't see if there's smoke or fog or rain sometimes. Some of the technology has helped to eliminate that, things like multi-echo. And the way that I look at multi-echo is, if you think about when you go to a shop window, you look at the shop window, you can see the window, you can see what's to the other side of the window. Okay, a net curtain, for instance, you can see the net curtain, but you couldn't see what's the other side of the net curtain. Some of the more sophisticated of these devices will see both of these. The less sophisticated devices will choose the strongest echo, and they will just give you that information. So as you spend more money, you get into areas where you have multi-echo functionality. The other thing is to take intensity information, so the intensity of the reflection. So if you imagine if you reflect something off a white surface, the intensity is significantly larger than it is from a dark surface. And if you get something which tends towards to a black body object, like for instance this lectern, LIDARs of any type would have difficulty seeing it because of the fact the reflectance of the light from it. Now, the better the optics are, the more powerful the beam. As I said, if you go up to laser class 2, then you can see further. If you increase the size of your device and you put bigger optics on it and bigger sensors on it, then you can see further. So these are some of the reasons why the Velodynes, the Regals and things like that tend to be bigger. Okay. The other thing is that these devices can be blinded by strong sunlight. So if you get a direct light into them, or you get another laser beam firing into the sensor area, then that can also create problems. The resolution, because these all work on steps, so they will take a laser measurement here, then it will move by a certain amount of resolution. So if your resolution is 0.125 of a degree, then at 30 meters or 80 meters, then that actually becomes quite a wide amount, okay? So you need to take into account. So if you've got a small object, like for instance, you're trying to see power lines, then what will happen is the laser beam, if you're too far away, will go over the side of it and you won't see them. So there's certain objects that you can see and certain objects that you can't see, depending on the capabilities of the LIDARs that you're using. And usually, achievement of 3D, if you're taking a multiplicity of 2D lasers, can be at the expense of time and money. So, for instance, when you're looking at robotics, you might only want 3D in a small area. You don't need 3D in a large area. So for instance, yeah, Velodynes and Regals are great, but who needs to see what's on the ceiling and who needs to see what's on the floor? It's redundant. And you could possibly say that instead of concentrating on getting the information from there, you could get more information in the interested area. But how do you define what the interested area is? If you're a robot or you need some sort of automation, then one person will want to look at a certain area, and one person for a different function will want to look at another. I mean, when we talk with each other, we tend to look at each other's faces, don't we? We don't tend to look sort of, not many people do, tend to look down or above their heads and things like that. So really the angle that you're looking at is only, that's the interesting angle, but other times then you need to be looking at a higher vertical angle. And what Hokuyo are trying to do at the moment is trying to define a 3D laser. It's going to be a slightly different approach, and it's going to be available at the end of this year. But they're trying to define a 3D laser which is suitable for, or is what the market requires. Not specifically, as I said with Hokuyo, not specifically for the geo sector, but more for the automation and the robotic sector. They've settled on the fact they're going to have a 40-degree operating window, 5-degree below horizontal, 35-degree above horizontal. Now, I'm sure from my experience that we're going to have customers out there who say 40 degrees is too little, I'd like it to be more, why are you making it 40 degrees? And then we're going to have customers that say, why are you making it 40 degrees? It's too slow, I'd like it to be 10 degrees or 2 degrees, or it's one of those things you can never win. And if you start putting in some automation which then allows you to control the vertical height, then you then increase the amount of electronics in here and the control things, and you make it bigger. I think these little 2D ones are perfect, but I tend to come from a robotics background, so I think they're great because whoever's doing the robotics can then move the sensor into whatever area they want to. But the geo market is totally different. You're looking for something totally different. So it's trying to get the adaptation and the way of meeting what the different markets require. So what's currently possible for Hokuyo? And I stress this is for Hokuyo. I know that for the other devices that are out there, then you can do a hell of a lot more. But we're talking about ranges of between 4 meters and 50 meters. Scan speeds of up to 100 hertz. Now that's pretty good to get 100 hertz in a sort of size footprint like this. Scan windows of 270 degrees with a blind sort of spot of 90 degrees. This is the processing time that's required. Accuracy is 1% of distance. That's not very, on paper, that's not very good. But the reproducibility that you get is significantly better than that. So if you look at some of the figures that Hokuyo get when they're testing the products, then you're talking about sort of 5 millimeters, 10 millimeters over 30 meters. So reproducibility is different from what you see as quoted accuracy, and accuracy can vary according to the substrate that you're looking at, etc. Resolution, 0.125 of a degree is our limit at the moment. The areas where we're strong, size and weight and power usage. I mean, this device here, 130 grams, it uses less than 5 watts. So if you want something like a drone, to put something on a drone, you want something on a mobile robot, then these can be your solution. If you're putting something on a Range Rover, and it's going cross-country, then you can put anything on it, a forklift truck, whatever. I mean, you're not limited there. 3D can be achieved and using intensity, information, and multi-echo functionality add to the detail and richness of what you see. Some of our customers, interestingly enough, some of the customers that are here prefer not to have multi-echo, and some of the customers that are here actually really like multi-echo, and it's quite interesting. So it's horses for courses. So there's no hard or fast rules. So what do we see the Hokuyo laser rangefinders, LIDARs, as being, in this market, they're part of the toolkit, they're a component. If people here are looking to create their own solution, they have a specific niche, then we can provide them with a component to do it. The area that we now sell into in this market are people like, as I say, GeoSlam, Navis, Createch, a lot of our customers who have developed their own solutions for their own particular requirements and for their own products. And they all have their own niche areas. There's no point in us reinventing the wheel in those areas. So we have a totally different take on this market, and in a way this is a new market to us. So it's interesting. Whether we will continue to try and develop it ourselves or whether we'll just let our partners do that, I don't know. Looking at what's available, really what we would see as being the top of the range that we've got available is a 30 meter, 40 hertz, although it is available in a 100 hertz version. 0.25 degree resolution, multi-echo functionality. But the important thing for us, or the sweet spot that we've got, is the weight and the size and the power consumption, because that allows it to be used in certain applications which other products can't be used. And the last little section on there is the proposed 3D scanner, which will be available later on this year. As I said, it's a totally different take on the way other people are approaching 3D. It is a laser beam which is moving up and down very quickly, 1.2 gig. So it moves very quickly up and down, and this up and down moving laser beam is being rotated whilst it's moving around. So what it produces is it produces a laser pattern which is undulating or going up and down, and then you can interleave that information so you can shift it so as to produce greater resolution at the expense of speed, or you can have it going at a lower resolution at a faster speed. So that's, and as I said before, we're talking about a 40 degree range, 5 degree below, 35 degree above. Not quite as light as we'd like it, so 750 grams, but it's still below a kilo. And we need to look to see what sort of market that develops and whether that's of interest to the market. It's, for me, it may be an area that we shouldn't be getting into, but we'll see. So that's the end of my presentation. I apologise for the fact it was so sticky to start with, and messing around with different devices and trying to get it transferred. Hopefully it's been of interest, and hopefully it shows a sort of slightly different take on the market, and it also shows the fact that Hokuyo have come into this market from a totally different direction from anybody else, really. But all these companies have approached these markets from different directions. I mean, and it's an expansion of the product range, and that's what happens.